All right, let's go ahead and get started. Welcome, and thank you all for attending this session. Hope you guys have had a great time here at Build and are pretty excited about Windows 8. One of the first things that Stephen demoed in his keynote about Windows 8 was that we've managed to pack in a whole bunch of new features in Windows 8 and still managed to have that core operating system footprint lower as compared to what we were in Windows 7. That's really exciting for us. That was one of the first demos that we did, and I'm really happy to see that some of our work got pretty well received among you guys. I'm Rahul Nair, and I'm part of the Windows Performance team, and with me is Joe Laughlin. We work on reducing the memory footprint on Windows, and also in developing some features which improve the responsiveness of the operating system. Being part of the Windows Performance team has given us a pretty unique perspective about memory usage, both from a holistic OS level and also from across all different layers of the software stack at a microscopic level. The first part of this session is going to talk about some of the things that we've learned and how we approach this problem in Windows and for Windows 8. And also how you as developers can apply some of those concepts to understand your memory usage. Then we're going to talk about the different ways in which you can allocate memory on Windows. It's just a basic high-level classification. We're going to also talk about using the Windows Performance Analyzer to collect and analyze some memory data. We're going to use some of the concepts that we discussed to look for areas where you can, just areas of opportunity for optimization. Then we're going to close and bring all of that together into some guidelines and best practices for both drivers and application developers. At the end of the session, we hope to leave you guys with an understanding of how to think about the memory impact of your application or driver. Like, how do you think about the cost? And also, how you can use the tools and leverage the tools to identify areas of opportunity for optimizing memory usage. Let's start with why memory is important. Memory is a key operating system resource, a key resource on the system, which ensures a really responsive and smooth user experience. A set of applications that are optimized in terms of their memory usage would mean consumers would be able to run more applications simultaneously while still delivering that really consistent and smooth user experience. Memory is also one of the key yardsticks with which consumers think about the efficiency of a particular piece of software. For example, in Windows 7, when people install their Windows 7 machines, the first thing that they did was boot up the machine, launch Task Manager, and see how much Windows is using. Like, how much is available for my apps? How much is Windows using? And if you remember from the keynote, we managed to pack in a whole bunch of features into Windows 8 and still bring down that core operating system cost. So user perception about resource utilization, memory is a really important part of that. You might have also seen from the keynote that Windows 8 is one of those releases where we're scaling to a diverse set of hardware platforms, different form factors, different configurations. Being lean and efficient in terms of memory footprint would make sure that your applications, your drivers, will scale across this diverse set of hardware and still deliver that really consistent user experience. Another aspect which people often do not draw a direct correlation to in terms of memory is power consumption. For example, like maybe 6 or 7 years ago, memory was getting really cheap, and all the PCs that were coming out had really ample amounts of physical memory installed. In the recent past, we've seen a shift towards PCs that give you really long battery lives and are really portable and mobile. Reducing memory usage is really key to delivering that experience. Another way to think about it is the more we can fit into physical memory, the lesser we need to go to disk, which means the lesser the cost there, which means better the power consumption. We've built engineering metrics around all of these aspects, and we've continuously measured that throughout the course of Windows 8 and look for opportunities of improvement. Memory is a pretty broad space. When we sat down at the beginning of Windows 8 to think about how to attack this particular problem, we came up with essentially a multi-pronged strategy. One that's focused on Windows and the operating system, and one that's focused on you guys, our partners, our developers, and our ecosystem. One of the things that we looked at throughout the course of Windows 8, and we continue to look at, is the idle memory usage. How much is the core OS consuming in terms of memory usage? One of the things that we looked at was the services that are running on the system. We thought, do all of these services need to be running all the time? Can we make some of them start based on demand and then go away once they're done? So if you remember from the keynote, we were at 29 processes on an idle system as compared to 32 on Windows 7. Some of those reductions came from making some of these services a demand start. We also looked at what we could do from a platform level to just improve the general memory usage on the machine. Just pool memory manager improvements, heap manager improvements, the process lifetime management. I don't know if you guys got a chance to go to that session. There was a session from Ben Strauer on process lifetime management. So it's just a lot of ways in which we look at improving general memory usage on Windows 8 from a platform perspective. So once we built that up, the next thing was, as more user scenarios and features came online, it was time to look at which are the user scenarios we want to optimize. For example, the new lock-unlock experience. Really cool, right? We want to make sure that that is as optimal from a memory usage perspective as possible. It's a scenario that we expect consumers to go through multiple different times a day. So we want that to be really optimal. So we looked at a lot of key scenarios. And once we built all of that, we wanted to see how it performs in the real world. And for the first time in Windows, we've actually built in telemetry capabilities into the OS. And what that's going to allow us to do is get a really microscopic level view of how memory is being consumed on the Windows platform. And we're going to use that, and especially so in beta, when we expect more people to use Windows, to get some of those signals from the real world and tie that back into improvements in the OS. What that also allows us to do is to reach out to you guys when we see opportunities, and we're going to do that through our regular communication channels when we find areas of opportunity. We've also invested a lot in making the tools really intuitive and easy to use. There's actually a session on the new Windows Performance Analyzer right after this one, so I would encourage you guys to go look at that. We're building assessments which help you measure performance on Windows in a really easy, intuitive manner. And there's also education around how you can think about memory usage and how you can approach optimizing memory usage. So we've learned a lot of things throughout the course of Windows 8. And we're picking a few key concepts which we've learned and applied while building Windows 8 so that you as developers can use that to optimize memory usage. We're going to talk about understanding your cost in terms of memory in totality, how that impacts system responsiveness, your impact over time, which is your short-term and your long-term impact, and things to think about in terms of allocation patterns. So first, let's talk about your application costs in totality. So when you think about the memory usage of your application or your driver, the first and really obvious thing that comes to mind is your files and your allocations. Those are your direct usage. You can relate to that. So remember that Windows caches files as well in memory, so that also contributes to your direct usage. One of the things that we often don't think about that much is your indirect costs. And what that is it could be APIs that you use. It could be system memory resources that you use. It could be the audio or media subsystems that you use for your applications. So in order to get a complete picture of the memory usage of your application or driver, you want to think about both your direct costs and your indirect costs. Once you've thought about that and you have a picture, you want to have some sort of gauge in which you want to focus your efforts for reducing memory footprint. And for that, we have a set of dimensions. First, you want to think about breadth of impact. How broadly is a specific feature set that you have going to be used, and what's the impact, right? The example here is like if you have a driver that's loaded on boot, the boot scenario is extremely critical, and you want to make sure that you're really optimal from that scenario's perspective. The second thing to look at is frequency of use. Do you think a particular feature set is going to be used multiple times and more frequently by your users as compared to others? You want to focus on those particular features. And lastly, you also want to think about what is your target audience and what's the platform you're designing for. For example, you think about designing a NIC driver for server as compared to having that on client. The requirements, the constraints are completely different. So you want to be really aware of your target platform and whether your feature set is applicable to that target platform. So that's application cost in totality. Next, we're going to talk about impact to system responsiveness. And to build that concept up, I'm going to first talk about composition of physical memory. So there's basically two distinctions, right? Things that are in use or actively being used, and things that are available for applications to consume. What comprises of in use? You have process working sets, including the system working set. You have non-paged memory, which is things that need to be pinned in physical memory. You have stuff that is modified that needs to be written out to disk. And then there's available, which is directly available for consumption. And that has the standby cache and the free list, which is just free. So the standby cache is really critical for ensuring system responsiveness. Why is that? I'm going to explain that with a high-level view of how Windows manages memory. I'm going to use Word as the example throughout. So imagine at the beginning of time, you have this pool of free memory. All of memory is free. You launch Word, which means Word is going to allocate a few things, and you have Word's working set in physical memory. And when Word deallocates something, it goes back to the free list. Pretty simple, right? Now you opened up a doc, you modified something on it, and what happens there is that goes to the modified list, which gets eventually written out to disk. Now imagine if you closed the Word doc. Where does that go? What we do is we place that on what's called the standby cache. And essentially what it is, it's a cache of things that were recently accessed by applications. And we hold that in physical memory in anticipation of the process needing it at a further point in time. So you wanted to go back to Word and change some other things. So you open that same document again. Where is it now? It's on the standby cache. And that's what we call a soft fault, which is just fetching something that's already in physical memory. If that document was actually on disk, then you have to do a hard fault, which is you have to go to disk to pick that up. And really the cost difference here is that a soft fault is really measured in microseconds, and a hard fault is measured in tens of milliseconds. So it's 10,000 times more faster to get something from the standby cache as opposed to the disk. Now think of a case where before you went back to modifying the document again, some other application came up, read a whole bunch of files, and then closed them. Where does that go? We put that on the standby cache as well. And what that could do is fill up the standby cache. And then what happens? You still need, standby cache is still available. If Word still needs to allocate something, we repurpose things from the standby cache. So your document, the document that you were modifying could actually be out of physical memory, and then Word would have to go to disk to pick it up. To summarize, the standby cache holds things that were recently accessed by applications, and it's really critical for system responsiveness. Two important considerations here. The higher your persistent memory usage, the less things we can cache. And if you have a large transient usage, that could push out things that were valuable for other applications or drivers that were running on Windows. The next concept is impact over time. We've used this concept repeatedly to characterize memory usage throughout the course of Windows 8. And really, it's two key concepts. Steady state, which is the bare minimum that you need to keep running as an application, and your peak, which is your scenario-specific allocations. Think about a Sudoku app, for example. Your steady state is really that first menu of clicking a new game or going to high scores or things like that. And once you click on a new game, you have a set of scenario-specific allocations that comprise your peak to start a new game. So really, you don't need to pay the cost of drawing the Sudoku puzzle as part of your steady state. So you want to distinguish things that are scenario-specific and things that are steady state. Again, tie that back to the standby cache. The lower your steady state, the more we can cache. And think about how frequently your peaks occur, which means If certain peaks occur more frequently, you're possibly pushing out things that we could have cached in memory. Here's an example. In the first chart, what question would you ask? You would ask, why is my steady state growing for this scenario? Right? Am I forgetting to free something? Why am I not getting back to my steady state once I'm done with my allocations? For the second graph, what would you ask? You want to ask, why is there a transient peak in memory usage for the initial portion? Right? These are the kind of easy questions that you can ask, and it's really intuitive once you get to the demo where we actually look at the tools and how they show the data. So that's peak and steady state. The last concept here is allocation patterns, which is what makes up your peak and steady state? It's your allocations, right? Ideally, you would expect a set of allocations to be made, which are your steady state allocations. Then you have some scenario-specific allocations, which you deallocate and go back to your steady state. This is really ideal behavior. Think of a case where you actually mix some of your scenario-specific allocations with your steady state allocations. Now what happens is once you free up those peak scenario-specific allocations, you're left with blocks of memory. If you look at both cases, we have the same amount of physical memory being used by the application in both cases, but not all of the memory is available as a chunk for the operating system. This is something that we've looked at a lot in Windows 8. This is what we call fragmentation. So it happens when you mix together allocations of different lifetimes together. So you really want to think about what are your scenario-specific allocations and what are your steady-state allocations, and make sure they're separated so that you reduce the risk of fragmentation. So just to summarize, we talked about the application cost in totality, where you think about your direct and indirect costs. Then we talked about the impact to system responsiveness and the importance of the standby cache. We talked about impact over time, which is your peak and your steady state. And we talked about allocation patterns that might lead to fragmentation. So those are the 4 key concepts that you can use when you're looking at and understanding the memory usage of your component. Next, we're going to talk about the basic classification of memory types. And for that, let me invite Joe on stage.
OK, so this is all going to be a lead up into the demo and how the tools present the data around memory footprint. So there are some basic memory classifications we need to keep in mind. There's 2 basic types, dynamic allocations and file-backed allocations. Dynamic allocations come in 2 basic flavors, pageable and non-pageable. And all dynamic allocations are things that don't persist across the invocation of the process or across the system boot. So that's a way to distinguish between dynamic and file-backed. So examples of pageable are things like heap and virtual alloc, or non-page pool, or non-pageable driver code. File-backed things are executables, your exes and your DLLs, your documents and your data files, and also, in some cases, driver images, for example, user mode drivers that get loaded like when you're printing. So let's talk a little bit in more detail about dynamic user mode allocations. For application developers, the most common type of dynamic allocation is going to be a heap allocation. The heap has 3 basic allocation areas. The mainline heap, which used to be the default heap before Windows Vista. Now all processes on Windows Vista onward use the low fragmentation heap by default. And the low fragmentation heap has some special attributes. I encourage you to go look at the Windows internals books to understand the low fragmentation heap in a little more detail than we can present here. There's some very good information in there that will help you understand some of the concepts in greater detail that we're going to talk about today. So one of the main things to keep in mind, the way the LFH, the low fragmentation or LFH works, is we will allocate a chunk of blocks. So for example, we may allocate 50 16-byte chunks that we're going to place allocations into. That is called a subsegment. The more outstanding allocations, the more subsegments we have. Those subsegments can either be completely full or they can be partially full. And we'll see in a little bit later, I'll discuss how the allocation patterns can lead to us having a large number of subsegments in memory that are partially full, and hence the fragmentation problem and how allocation patterns interact with that. The other thing that can happen with heap allocations, if they're over a certain size, which is 512K on a 32-bit process or 1 megabyte on a 64-bit process, the heap APIs will actually hand those allocations off to virtual alloc. So even though you call things like new or malloc or the heap APIs directly, the actual allocations will still be done by virtual alloc. It's also possible for applications and things like user mode drivers to call the virtual alloc APIs directly. And they're also used extensively in things like the graphics subsystem, so typically for large buffers. Dynamic kernel mode allocations also can occur in multiple places. Since this room is probably mostly composed of driver developers, I would expect you're already fairly familiar with the pool. So there's the page pool, which is, of course, for pageable allocations. There's the non-page pool for non-pageable allocations, and these things are essentially pinned in memory, typically used for things that access either via DMA or at DSR or IPC level. Something new that's been introduced in Windows 8 is the non-execute non-page pool. This essentially has the same functionality as the non-page pool, but all the allocations are guaranteed not to be executable, and therefore they cannot contain code. We would encourage you, as you're developing drivers for Windows 8, to take advantage of the non-execute non-page pool whenever possible. And if you do have cases where you are putting code in non-paged allocations, that you try to find a way to not do that in the future, because it does have memory consequences. So for example, now in Windows 8, we're going to have both the executable non-page pool and the non-executable non-page pool, and we can end up having additional costs as a consequence. The last pool type is session pool. This is used for session-specific allocations, typically for graphics type allocations, but also for devices which are shared cross-session, like mouse and keyboard. So all of the memory data that's going to be presented in the tools has some very consistent information across all of them, but there's also some context information that's specific to the allocation type. So the basic data is how big the allocation is, when it was allocated and when it was freed, which is the lifetime, the allocation stack that it was placed on, which also includes information like the thread ID and the process ID where appropriate. And last, but one of the more important ones, is the address, where within either the user mode or the kernel mode address space the allocation was actually made. There's also a bunch of metadata, and this metadata, again, is based upon the allocation type. So for example, for heap allocations, you would get the heap handle that it was placed in. You would also get things like the subsegment and the low fragmentation bucket size that the allocation was placed in. For pool, you're going to get the pool type. Was it pageable, non-pageable? Was there some special attributes that made this allocation different? For example, is it a contiguous non-page pool allocation as opposed to just an ordinary non-page pool allocation? And in the pool, we'll also get the 4-character pool tag. And there's also some context information. Was this a long-lived allocation relative to the range of the lifetime information that's being displayed in the graph? Or was this something that was allocated and then freed, or in other words, transient? So let's move on to the demo. So in the interest of time, I've opened up a pool trace and loaded it into WPA, and I've already done some things to load symbols. And this is the new UI for WPA. If you're familiar with XPerf View, this presentation of the data is going to be quite different. As Raul mentioned, there is a presentation on the WPA tools immediately following this session, which I would encourage you to attend. So if I drag the analysis view over here, I'm going to get a graph. And then I can open the summary table. And I see lots of different information here. Now, the nice thing both about WPA and the XPerf plugins that you're probably familiar with in the past is in the summary table, if you rearrange the columns, you can get a drill into the data that's going to be more actionable for you. For driver developers, you can look at all of the pool allocations that are made across the entire system, but for you, you're probably more interested in the things that's specific to your driver. So I can drag the pool tag module all the way over to the left, and I'm going to have to do that. So in this case, now all of the allocations are filtered by driver. And I can click on a particular driver, and I can do some filtering up here. So I'm going to do that. So first thing I'm going to do, I'm going to disable all the series. And then I'm going to look for my particular pool tag module, which is my driver, which is this one. And then I can say, show me only the allocations. I did do that already. Okay, the demo gods are not working well with me. But what this should be doing is filtering it out to just the allocations that are made by my driver. And you can, if I hover the mouse over it, you can see that these are the allocations that are being done by this test driver. And if I open this, you can see some conspicuous pool tags here named leak. And if I open that up and then I drag the stack column to the left of the gold bar, I can aggregate. And I can pop these stacks open. And now I can see the allocation stack for the allocations in the tool. So I can immediately drill into not only just my driver, but by pool tag, and then by stack for that particular pool tag. So it's really easy in the new tools to not only get a graphic representation that's unique to the area of interest for you, but also to quickly drill into the things that are most impactful. I encourage you to experiment with different column arrangements because this is the real power of the tools. Different column arrangements give you different insights into the memory usage of your particular driver or application and can help you identify areas of opportunity. So that's the basic idea. There's also some recordings that are available online, and I believe they're on your DVD that go into more detail about the tools. So what are some guidelines and best practices you should be thinking about when you're investigating the memory usage of your products? So as Raul mentioned, we need to understand the peaks and steady state, know what you need long-term, know what's transient, and think about this from a mental model. I'm doing this operation. I think it should take this much. Is this the same type of cost that I'm seeing in the tools? If it isn't, obviously you need to do some additional investigation to figure out where the discrepancy is. Sometimes you'll find out that that really is the cost. It wasn't what you expected it to be. In some cases, that means there's an opportunity for improvement, and sometimes that means you need to shift your mental model a little bit based upon what the actual usage is. But the key point, like Raul mentioned, is minimize your steady state. Anything that is scenario specific, after you're done with it, you want to release it. So there's some additional questions you should be asking yourself. When do I allocate things and when do I free them? Right? It's very important not to pre-allocate things that you don't need or you're not sure you're going to need. Right? Inside Windows, we call this pay for play. If you're not going to use it, don't pay the costs. And last, allocation patterns are important. Right? So let me give you a concrete example. One of the things we discovered when we were investigating the Windows memory usage was that when processes were created, we would create critical sections in all the places where we needed to control the access to certain data structures. Something we can't avoid. Obviously, we need those there for correctness. However, the critical sections, when they're created, result in two different types of allocations. There's an allocation for the critical section information itself, but there's also an ancillary allocation, which is used to contain contention information for that critical section, and also some debug information. It turned out that this ancillary allocation was the same size of something that was allocated during the transient, was during process creation, was the same size of a large number of transient allocations. So I mentioned earlier about subsegments. So we had all of these transient allocations, which would create a whole bunch of additional subsegments because what was already there was full. So we had to create additional subsegments to handle these allocations. But these were all transient, in other words, short-lived. But these allocations for the critical sections had to be there for the lifetime of the process. And so we were leaving these allocations in all of these subsegments that were created to handle the load of these transient allocations. So when we freed those allocations, none of those subsegments could be released because those long-lived allocations from the ancillary data structures for the critical sections were there. They weren't big. They were just somewhere in the neighborhood of 24 bytes each, but there was a large number of them. Total size was somewhere around 150 to 200K. I don't remember the exact number. So what we did, instead of creating those allocations when we created the critical sections, we deferred those until they were needed, either because you attached a debugger to the process or the critical sections became contended on and we needed to keep that information around. Even though we only reduced the number and size of the outstanding allocations during process startup by about 200K, we saved over a megabyte. And that was part of the improvement that you saw during Stephen's keynote. So allocation patterns can often be as impactful as either not making the allocation at all or doing it at the wrong time. So let's talk in a little more detail about some best practices. Okay, please use the tools to understand your pool usage if you're a driver developer, because that's probably going to be where most of your allocations go. As Rahul mentioned earlier, focus on your most frequently used scenarios and also your steady state usage. For example, if you're a boot start driver, what is your footprint on the system immediately after booting the system? Non-page pool is particularly important because it's always there. So that's part of the baseline steady state usage of the operating system. And again, don't pre-allocate things that you're not likely to use. Right? That's a consistent problem that we've seen across drivers, not only Microsoft authored drivers, but also third-party drivers. And make sure you're laying out your data structures efficiently. Keep in mind that you're going to be running on both a 32-bit architecture and a 64-bit architecture. So if you do things like pointer int, that's probably certainly acceptable on 32-bit architectures. 64 bits, we're going to have padding, which we want to avoid. Again, I can't overemphasize enough, intermingling long-lived and short-lived allocations can often cause costs that we don't want to have to pay. For application developers, again, please use the tools to understand your memory usage. You're often going to be surprised, as we were, about some of our allocation patterns and some of our usages, and use them to identify opportunities to go off and make improvements. Focus on the most frequently used user scenarios, and be conscious that you need to test things in different order. If you have 3 different operations, Operation A, Operation B, Operation C, measured in that order, then measure it C, B, A, B, A, C, right? And the reason for that is the allocation patterns will be different, and your steady state usage at the end of those operations may be different as a consequence of executing them in different order. So that's something very important to look at. Again, defer memory allocations until you need them, pay for play, and ensure that all of your scenario-specific allocations are freed as soon as possible. So for example, if you print, which is typically a memory consumptive process, When you're done printing, free up those buffers that you were using to send information to the printer as soon as you're done. Raul? I'm going to hand back to Raul for the closing and key takeaways.
All right. To conclude, memory is a really, really important resource, both in terms of allowing the operating system and the applications to scale across a diverse set of hardware platforms, still delivering a really consistent user experience, and delivering the long battery life that all of you guys really like. It has a direct impact, like how much you use as applications and drivers has a direct impact on system responsiveness. So when you want to use some of the concepts that we've discussed to go and understand the memory usage and invest in making improvements. Think about the different questions that you can ask. The tools make it really easy for you to ask those questions. What's your peak, your steady state? How efficiently you can manage your allocations? What about allocation patterns? Are my allocation patterns susceptible to causing fragmentation or not? So use the tools to ask all of these questions. A set of really good memory optimized applications and drivers will make the experience of Windows 8 that much better for our consumers. So I would want to actively encourage all of you guys to invest in understanding the memory usage, utilize the capabilities of the tools, and make Windows 8 a really good experience for our consumers. With that, we'll open it up for questions. Sure.
Regarding the NX driver and the NX tools, how are we supposed to make the change there? Is it being done by NX itself, or exposed by NX?
So the question is, for the NDIS driver, how are allocations going to be moved on to using the NX pool? So we've done a lot of things to move all of our inbox drivers to using NX non-page pool. We also have some capabilities and macros in the code that will allow for compatibility across Windows 7 versus Windows 8, where this capability is not available. We're identifying partners where they can make this change and where applicable. And we're going to make it really easy and document it so that you guys can easily move over your allocations to NX.
We need to do the actual review of our allocations, and we have the actual ability to go off and make these settings. It's not something that NDIS handles for us.
If NDIS is making the allocation itself, depending upon whether they know whether they're going to have a compat problem by moving to NX, they'll probably just use NX by default. Oh, I turned it on. Okay, can you hear me now? Hello?
The other way.
There it is. Okay. So the NDIS driver is going to have to make a decision on whether or not they're going to have a compat problem if they automatically use NX by default. I don't know off the top of my head what that decision is, but if they believe that they're not going to have a compat problem, they'll probably just use NX by default. I'm sure this is going to be something that's going to be documented, and so I would encourage you to watch MSDN and to understand what the final decision is.
Sure. You want to use the mic so that.
Memory allocations by drivers, are you adding any certification requirements regarding driver memory utilization, and are you adding any tests around that in the logo?
So we actually have a couple of requirements in the Windows certification program. Most of that is focused on the non-paged or the persistent pinned memory cost of drivers. So we're looking at the amount of code, non-paged code that's in memory. We have a few bars around what's expected. We've collected data on how much code drivers have in the wild, and use that to come up with certain bars. We also have a cap on the MDL allocations and contiguous memory allocations that drivers make. So all of that's going to be available via the LogoKit documentation. So that's the two memory-based requirements that we have. We also have a requirement around, it's not a requirement, it's more of guidance around NX. So you can have your drivers test for what allocations you make in executable non-page pool, and it's going to tell you that you might want to move some of those allocations over to NX. So that's not a hard requirement, it's more guidance.
It is a hard requirement, though, for the new ARM platform.
For ARM.
The only non-page pool that is available there is NX non-page pool.
And so am I to understand from what you said that all of them are not actually tested? They're hard guidance, and for ARM it's really hard guidance, but it's not actually tested as part of the WCAG tests.
There are tests. There's the assessment ADK, and there's also the Windows Logo Kit certification tests.
Which will actually check our allocations.
Yep, it's a hard requirement in the logo certification process.
And there's a difference for the an ease if you use NX pools instead of non-NX non-page pools.
The logo certification test for NX versus non-NX is just meant to provide guidance on where your allocations are at. It's guidance, it's not a hard requirement. It's, we don't want you to rev all of your drivers for previous versions of Windows, because of compat reasons and testing and all of that. So it's more meant to be guidance. For ARM, however, it's going to be a hard requirement.
But it's not like you'll get a larger allocation permitted with NX pools than with regular non-page.
No, NX
right?
is really a security feature, right? So that we can't have executable code in pool. It is not about enabling you to make larger allocations. We're still concerned about the size of the allocations themselves.
Thank you.
How can I practically avoid defragmentation by not mixing long-term and short-term memory allocations? Do I have any control over where the memory manager would allocate my chunk of memory other than just specifying the pool?
In the case of pool, you don't. So you need to be conscious about when you allocate them and how your driver interplays with other drivers on the system. That's not always an easy thing to do. We understand that. So there are some things that you could do. If you know you're going to have allocations for a particular pool tag that are going to be repetitive and frequent, all of which are the same size, you could use things like a look-aside list, or you could allocate them once and then reuse. Those would be the guidances that we would have in these particular cases for the pool.
You can also use the tools to see across how many pages are your allocations spread across. And that's kind of an indicator on whether you're susceptible to fragmentation or not.
So to give you some additional information, if it's a large pool tag, a large pool allocation, which is a pool allocation that's a page or larger in size, typically those are going to be the allocations that are going to be more causes or potential causes of fragmentation. If it's a small pool allocation, which is an allocation that's less than a page in size, if you're less than 2K, you're more likely to be a victim of someone else, some other pool tag fragmenting the system. If you're larger than 2K, obviously you can only place one of those allocations within a page. So if there's not 2K available on a page that's currently being used in the pool, we're going to have to commit an additional page in the pool to handle that allocation. In that case, you may be one of the causes of fragmentation.
You were mentioning look-asides. Are those per driver? Are they mixed together? Which means that if there is two drivers that want to create look-asides of the exact same size, are they going to be the same thing as far as the operating system?
You can create your own driver-specific look-asides. So those would only be for your own tags. So we would encourage you, if you do make use of look-aside lists, that you be conscious of how many allocations are contained on those look-aside lists, and if your driver is not active for a length of time, that there are APIs to cause the look-aside list to be drained, and we would encourage you to do that.
Follow up on this: if they are tagged by different
The question is whether or not multiple tags can be placed upon the same look-aside list. They can. The look-aside lists are size-specific. So if the two different pool allocations are similar size, they could end up on the same look-aside list.
Any other questions? All right, so there's a, as Joe mentioned, there are a bunch of videos that explain how to look at heap and virtual alloc in the same way that we've looked at for pool in this demo. We'd also encourage you to attend the next section, which is on Windows Performance Analyzer by Michael Milrood. So that's going to help give you a better understanding of the new tool and the new UI and its capabilities. Thank you all for attending. Hope that was useful. Enjoy the rest of your day.